So the topic of today, section 6.3, is going to be ratios is the main topic. And ratios expands pretty quickly to other things, but we've already talked about ratio back in chapter 5 as one possible physical reality for fractions. And all a ratio is a comparison between two numbers with division. And a ratio that we talked about before would be like male to female. Come on, pen. There you go. So for example, in this class, there are 5 males and 8 females. So the male to female ratio is 5 to 8. So sometimes this is read as 5:8 or 5 to 8. And those are just other ways to state ratios. So sometimes a colon goes in between, sometimes just the word 2, but it really is a fraction, male to female. Other kinds of ratios, like think about this for a second, other ratios you use in your life. So for example, some I use in my life is I like to make pizza sometimes. I make my own pizza dough, and to get the right, crust, I need a good flour to water ratio, so it's not too wet or not too dry. And for the flour I use, I find 3 cups of flour to 1 cup of water works pretty good. So that's one I use once in a while. There's some other breads I make that might be a little stiffer than this, others that are a little wetter, just kind of depends. And the flour matters too, so that's not like for all pizzas, depends on what kind of flour you're using and maybe what other ingredients you have. Other ones that have come up, I did construction to get through college and periodically in summers between teaching. And so something that comes up common with construction are similar figures and making shapes, some geometry. For example, I might need to make some triangular roof braces, and they always have the same base to height ratio. So maybe the ratio of base to height is always 5 to 4. So I get a consistent pitch when I'm making that happen. Slopes of things you may have come across. So just kind of curious, can any of you think of some ratios that might pop up in your life on a regular basis?
I'm still thinking.
All right, you guys keep thinking on that. So I'm going to ask this again later because we're going to look at a couple of different kinds. So think about where ratios come up in your life, and I'll probably jog your memory to that in just a minute. Now, some ratios are called rates. So a rate is a special kind of ratio. And a rate is a ratio with different units. So common rates that we come across is most of us drive a car or a bicycle or something like that. So like miles per hour. The word per literally means divide, right? So that's miles divided by hours. So that's a common rate we might use. The flour and water for my pizza, those are both measured in cups, but I also put yeast and oil and sometimes other things in my pizza. So if I look at, say, flour compared to yeast, that would be more of a rate than a ratio. even though a rate is a ratio. So like my flour to yeast, I would call that a rate instead of just a ratio, because with my 3 cups of flour, I'm probably going to put in 1 tablespoon of yeast. So since they have different units, it's called a rate, but it's still a ratio too. Another one, when I go to the store, sometimes I look at the labels, like if I'm comparing 2 boxes of graham crackers, and I want to like, which one has the best dollars per gram or dollars per ounce thing. So that might be one we might look at, like dollars per ounce, or maybe dollars per gram. For example, let's see, I was just looking at my chocolate bar I was snacking on before class, and I'm not ready for that page. My chocolate bar, chocolate bar. It was a fancy chocolate bar with cocoa nibs and quinoa crunchies in it, and it cost $5, a little on the pricey end for a chocolate bar I usually buy. And it was 2.5 ounces of weight. Right? So that would be the rate, dollars per ounce of the chocolate bar. Sometimes we measure things in grams. So that 2.5 ounce chocolate bar is also said to weigh 70 grams. So I can give that ratio either way. Now, sometimes we actually carry out this division. Like, what is 5 divided by 2.5? So let's see, 5 divided by 2.5, that's what, 2? So that would be, I could also write this one here as $2 per ounce on that one. This one, dividing by 70, 70 is a pretty big number compared to 5, so I might rethink that one right there and call it like 500 cents divided by 70 grams, because sometimes when you go to the store, they talk about, you know, cents per ounce or ounce per cent. So in this case, what would that be? That would be 50 divided by 7, which is 7.14-ish. So 7.14 cents per gram. So maybe on the label at the store, for comparison, they often list like dollars per ounce or dollars per gram, so you can compare two competing brands to see which one might be a better deal in that way. So those are other ideas of rates that we might come across. So talked about some ratios, some rates. Anybody else come up with an interesting idea that they've come across recently in their life for a ratio or a rate? Is it Monday or something? You guys are awfully quiet. I think we might have to have a contest. Who can come up with the most interesting one and it's going to be worth extra credit? Will that get me some input here?
Cars to trucks.
Oh, what's that?
Cars to trucks.
Cars to trucks. Like when you're hanging out in Hermiston or Pendleton, Eastern Oregon, we're going to have a lower car to truck ratio on this side of the state than the other. That's a good one. I love that. Here's one that I came across recently for a rate. And am I ready to talk about this one? Oh, one more example, and then I'll talk about that. Here I was looking at ounces versus grams, right? 2 different ways to measure the weight or mass of our food and other things. So it looks like, based on the packaging I got, that for every 70 grams, there are 2.5 ounces. And we could clean that up a little bit. So what's 70 divided by 2.5? Let's get a calculator. 70 divided by 2.5, 28. So according to that, that would be the same, right? I did the 70 divided by 2.5. That gave me 28, and that would be grams per ounce. Another way I could write that is that since I did the division, that would be 28 grams divided by 1 ounce. So it looks like 1 ounce is pretty close to equal to 28 grams. Look that up. Ounces to grams. What does the all-powerful Google say? All-powerful Google says, yeah, it's a little over 28. Okay, so they didn't show the decimals on the package. It's pretty close though. Okay, that's cool. So unit conversions are another places these rates come into play. All right, so with that, I'm going to tell you an interesting story from a couple years ago. Just one button. I need to draw a picture to show it. So I live in Pendleton, and Carnival comes to town, or used to come to town, a few times a year. Haven't seen it yet in the days of COVID. Kind of bumming about that. But I used to like the crazy rides. I don't anymore. But one ride I always like to go on is the Ferris wheel. So here is my version of the Ferris wheel. Something like this. This little triangular strut holding it to the ground. And then I like to sit in the car here and wave at all the peoples down below. Hey! And this thing goes round and round and round. And so I'm riding this thing, and I get to the top, looking out of the city and all the people, and then I thought, oh wow, I wonder how fast I'm moving as I'm going around here. Okay, so this motor's turning this thing, I'm going round and round. I was like, okay, I think I can figure this out. So I pull out my phone and I get my stopwatch out, and so every time I get to the bottom, I click my stopwatch. And so I did that a few times, trying to get an average time going around. And it took 15 seconds to go around. All right. So 15 seconds to go around. So I want to know, what is my speed here? And so I'm just going to use some ratios to figure this out. And so follow along with me. This is kind of a fun problem, because you can do this yourself and impress your friends. So I did that a few times, right? I got the average time going around with just the stopwatch on my phone. A regular watch would fine too. And then I wanted to figure out my speed. Well, what is speed? Speed is distance, that one, over time. And I've got a time going on here, but I don't have a distance yet. So I want to come up with a distance. Well, they weren't about to let me get a tape measure and measure around this thing, which is what I want to know, right? I want to know how far is it around, right? Because that's what I'm traveling. I'm traveling on this circle. It took me 15 seconds to get from here back to there. So I need to figure out what that is. All right, well, it's a circle, right? So what do I know about circles? I know that the area of a circle is pi times the radius squared. That's not what I want. Circumference, that's the distance around. That's 2 times pi times the radius, or just pi times the diameter. Now, I mentioned this, did I mention this last week? No, I didn't get to mention this yet. I'm going to mention this week. If you think about this, c equals pi times the diameter, what that also tells us is that pi is equal to the circumference divided by the diameter. Pi's are interesting, kind of weird number, but any circle, if it's perfect, and you perfectly measure its circumference, perfectly measure its diameter, and you divide those two, that's where pi comes from. It sounds easier than it is. People struggled with this for thousands of years. They realized there was something special there, but actually finding the value of pi, we're still working on that, because as a decimal, it goes on forever, which is freaky. Anyway, that's a side story. We'll get back into the next section, section 6.4. Right now, I need to figure out what the circumference is. So I'm pretty sure I can measure the diameter of this thing by just walking outside of it and eyeballing, where is this edge, where is that edge, and I have the good fortune that most of the shoes I wear are almost exactly 12 inches from heel to toe. So then after I got off this ride, I heel-toe walked from this side over to that side over there and guessed how many feet it was. And I found that this one was 50 feet. in diameter. So I get this 50-foot diameter circle. Now I can figure out its circumference. So its circumference has to be pi times 50 feet. Now, I had my phone calculated, but I'm just saying, well, you know, pi is about 3. 3 is a nice easy pi, so that's around 150 feet. I could do better than that, but I'm just going to call it 150 feet. It's around that. And I did double check, by the way, this because there were bricks in the sidewalk in front of this. And I figured out the bricks were 8 inches. And so I counted the bricks too to double check my 50. So I had a backup plan there. All right, so what do I got now? I have that I covered 150 feet, so I got my distance. And it took me 15 seconds to do so. And cleaning that up right there, 15 goes into 150 10 times, so I'm moving at 10 feet per second. Now, that's a common measurement like in a physics class and in some other places, but I'm used to thinking like miles per hour. How many miles per hour is that? Okay. So next cool thing, we can figure that out. And to figure that out, we just need to know a few things like how many seconds are in 1 hour and how many feet are in 1 mile. Does anybody know either of those facts?
Isn't it like 5,297 for feet per mile?
Oh, you're so close. You're a little off by like 17 feet.
I think Jimmy got it.
Oh, no, a little, you're off by 500 feet. There we go, 5,280, yeah, thank you. 5,280 feet. Now, as far as seconds in an hour, there's 60 seconds in a minute, 60 minutes in an hour. So that would be what, 6 times 6 is 36, 10 times 10 is 100, 3,600. So what we can do are unit conversion ratios based on these equations here. So I'm just going to take my 10 feet per 1 second here, and I'm going to multiply these suckers by unit conversion ratios. And color, here we go. So I want seconds to go away, so I'm going to put it in the numerator, which puts hours in the denominator. And the point is, you can think about seconds as an actual number. Seconds divided by seconds, a number divided by itself kind of vanishes. It becomes a 1. And if I know that there's 3,600 seconds in 1 hour, since this is in the numerator, it's going to tell me to multiply by 3,600. And then conversely here, I have feet in the top. To get rid of it, I have to put it in the bottom of a fraction I multiply by, which puts miles in the top. And I know there's 280 feet in 1 mile. And because this is in the denominator and a fraction bar means divide, this says I'm going to divide by 5,280 to get rid of feet. So in my calculator, if I just take 10 times 3,600 divided by 5,280, that should give me an answer in miles per hour for my speed moving around this Ferris wheel to the best of my estimation ability. So let's see what it is. 10 times 3,600 divided by 5,280 says I was moving at almost 7 miles per hour. So that's a fast walk. So that's a pretty quick moving Ferris wheel. So if I were trying to, like at the bottom, jump off while it was moving, I would hit the platform moving a little faster than I would normally walk. Like maybe, I think most people walk like 4 or 5 miles per hour, if I remember right. So this says I'm moving at about 7 miles per hour. Kind of cool, huh? So this is all this is using ratios and rates to do some awesome math. Just an observation of moving around Ferris wheel. Fun stuff. All right, so that is an example that takes into account much of what we're doing in this section. And a couple more topics before we get into percentages. Proportions. So a proportion is when you have two equal ratios or rates. Two equal ratios. So for example, I know that 1/2 is also equal to 5/10. So that would be a proportion. Often we use proportions to solve for a missing number. So for example, if I'm thinking about my bread recipe, where my flour compared to my water is always 3:1, and I happen to have 7 cups of flour, I can figure out how much water I would use. This kind of goes back to our cutting cakes like the other idea. So if I take the 10s and multiply them over here and the 2s and multiply them over there, 10 times 1 is 10, and 5 times 2 is also 10, right? So that's an indication that my proportion was correct, equal in the first place. And I can apply that same strategy here to the missing one, with a little cross multiplication. So that leads to a new equation, 3 times question mark is equal to 7 times 1. And then we can divide the 3 over to finish it off. And so my question mark, missing number, must be 7/3. Now this is in a situation where in a recipe, 7/3 is an awkward kind of number. Oh, it's a lovely number. It's reduced. A mixed number might be better. 3 goes into 7 twice and 1/3 left over. So I would need 2 1/3 cups of water as opposed to 7/3 cups of water.
Aren't most measuring cups, they would do it in thirds anyway? I've never seen one that has 7/3 marked on it.
Yeah, the biggest measuring cup I have at home is a 2-cup measuring cup, and it goes into, it doesn't say things like 1.5. It's sorry, 3/2. It would say 1.5 cups, right? Yeah, so it's most things like, again, we talked about this before, 7/3 is reduced, 2 1/3 is reduced, 2 1/3 is more common in our communication in this country than 7/3 is. 7/3 is nice if I need to do another calculation, like I need to use that water calculation to do something else. Then I would like the 7/3 better. A note about playing with proportions. Often what I do is if I know the missing thing is water, I would instead write it as water over flour. That would be 1:3 for the ratio. Now the missing number is in the top. And then really all I need to do to solve this now is take this number underneath the missing number and multiply it over. So my missing number is whatever 1/3 times 7 is. So sometimes we can engineer the proportion to be easier to solve. So rather than having to cross multiply and then divide, it could just be a multiplication if you set it up right. And the catch there is put the missing number on the top. And then it's a little less work. Right, so there, I just have to think about my setup, and I have less math to do, if you don't count setup as math. I guess setup is kind of the math there too. All right, let's look at another example of proportions. I mentioned similar figures earlier. And so let's take a look at, and it can be really any figure at all, but I'm just going to pick on triangles because they're the simplest kind of figure one can make. So let's suppose, like earlier, I said I had a triangle that had a base of 5 and a height of 4. 1, 2, 3, 4. That's the triangle I want. So that'd be a pretty steep roof, but again, here's my 5 base, and here is my 4 height. Now, if I make another triangle inside this, like suppose I stop at the 2 here and I need to make a triangle with the same shape, but I only want it to be 2 for the base, I want to know what that height is right there. And it turns out if they're the same shape, and in math, same shape, the word for same shape is similar. We'll look at this some more next quarter. Then if I take ratios of the same sides, meaning I always write height over base as my ratio, the original triangle had a height of 4 compared to a base of 5. My new triangle has a height of I don't know what to a base of 2. Now, since the missing number is in the top, I don't actually have to cross multiply and then divide. I can just take this 2 and multiply it to the other side. So then my missing number is going to be 4 times 2, or 8, divided by 5. And 8/5 is a nice number, but most people would prefer that as a mixed number or a decimal. So 5 goes into 8 once with 3 left over. 3/5 would be 6/10, so I could also say it's 1.6. And if I drew my picture well, that should look around 1.6. And that's not too bad. It looks a little tiny bit high, but it's pretty close. It looks reasonable. It's under 2. So my picture is not too bad. So my picture looks like it was drawn roughly to scale, and this measurement makes sense in my picture. So a ratio of 4 to 5 happens to be the same as a ratio of 1.6, 1.6 to 2. Could I have written it as base over height? Yep, could have. That would have been just a little bit more work, but I would have gotten the same answer. So just to demo that, if we didn't think about the order of these mattering, which is in the top and which is in the bottom. And by the way, when you're working with proportions, I highly recommend you always write one fraction that says what's in the numerator and what's in the denominator, because if that gets mixed up, everything goes to hell. So here, my base is 5 on the original, the height is 4. In the new one, I have a base of 2 and a missing number, we can call that x if we wanted to. And in this case, since the missing number is in the bottom instead of the top, I actually have to do the cross multiply and then divide. So cross multiplying, I get 5x equals 8, and then I can divide by the 5 and get the same answer I got before. So I do think it's worth taking a moment and saying, what should the numerator be? Because it can, if we think about the setup ahead of time, lead to easier math. And there's nothing wrong with easier math. Why make things harder than they could be? All right. So those are the big ideas I had about what is, again, the big things here were, what's a ratio? And all the ratio is we just divide 2 numbers, okay? Now, point is those numbers should have some meaning, like males to females, flour to water, base to height. If they have different units, like miles versus hours, or cups versus tablespoons, or dollars versus hours, then those ratios are also called rates. So a rate is a ratio, but with different units. We can then use those ratios or rates to create other ratios or rates, and those are called proportions. And all a proportion is when we take 2 ratios and set them equal to each other. Okay? And usually we do that when we're missing one of them. And I would say the majority of math that comes across our path in life is a proportion. That's the math most humans do most often. So having a good grasp on proportions is super helpful. All right, next. So I've got these grids here for a reason. Kind of just playing around with my toys here. We're going to take a look at percent next. And we're all pretty familiar with percents. We use them in a lot of different contexts. But I just want to kind of break down what percent means, and it might make things easier to deal with percents. Then we'll get to some harder problems. So the word percent literally means per divide cent 100. divide, like miles per hour, miles divided by hours. Cent means 100. So percent per, it's divided by cent is 100. Now, if you think about the symbol, so let's just come up with an example, like say 35%, right? That's the symbol for percent. This slash is the division, and these two little circles are the zeros from 100. So historically, this came from bookkeepers way before computers, right? Hundreds of years ago. Instead of, they were always dividing by 100, or often they get tired of writing divide by 100. So this became like a lazy version of divide by 100, 35 divided by 100. Right, so this is the lazy version. And it caught on, and people started writing it more often. Yeah, percent, I love that symbol, it's cute, let's go with it. So again, that symbol literally means divide by 100. So 35% really means 35 divided by 100. You could use that symbol. 35 slash 100, 35 over 100. The symbol means divide by 100, however you choose to write divide. Now, as far as that division, we could think about it in terms of decimals. So we have a couple options here. We could think, oh, divide by 100, that's a decimal fraction. In which case, we know that the second place is the hundreds, so this must be 35 hundredths, slang 0.35. We could also think about it as a fraction and wonder if we can reduce it. And 5 goes into top and bottom, so I could take that 35 over 100, divide the top by 5, divide the bottom by 5, and that gives me 7/20ths on a good day. That's good. So there's two ways to reduce percents. You could just rewrite it as a decimal, because percent means divide by 100, and so there's the hundredths place. Or you could reduce it as a fraction. Now, they don't always reduce. For example, 1% is 1 out of 100. Doesn't reduce. Sometimes they reduce, sometimes they don't. These squares are here because it's really nice to use a 10 by 10 grid representation for percentages. So if I wanted to illustrate 35%, I would just have to shade 35% worth of this grid here. So I've got 1/10, 10% there, another 10th, 10% here, another 10th, 10% there. There's 30%, 1, 2, 3, 4, 5, right? So that right there would be my 35%. 1%, that's just 1 out of these 100. Right? Maybe this one right here. I can even do something like show, maybe in this one over here, 12.5%. So there would be a whole 10th. 2/100ths, and then just try to show half of one there. So that's my illustration. I'll try to outline that of 12.5%. So percents are fractions ultimately, because the percent symbol does mean divide. So when I'm thinking about writing down percents, I have basically three options. I can write them as a percent, meaning using the percent symbol. I can write them as a fraction by using divide by 100, or I can write them as a decimal by taking that fraction and putting it in decimal notation. And sometimes this goes really well, sometimes it's a little weird. Like think about when we were playing around with decimals versus fractions in the first section of this chapter. Some fractions make awkward decimals. Pretty much all decimals make nice fractions though. It usually goes well the other way. So I'm just gonna make a table here, illustrate a few examples, give you a few to look at. So for example, we already looked at 35% as a fraction is 35 over 100, but also reduces to 7 out of 20. As a decimal, 35 hundredths. And again, remember, try not to use the slang as often as possible. 0.35, 35 hundredths is better. 1%, 1 out of 100, doesn't reduce 1/100th. And we could go other ways. Instead of starting with a percent, we could start with a fraction or a decimal and go back. Like suppose we had the decimal 55 hundredths. Well, that's pretty straightforward decimal. I could rewrite it as a fraction if I read it properly, 55 over 100. I could reduce that if I want. 5 goes into 55, 11, 5 goes into 100, 20 times. Decimal to percent is usually pretty straightforward. That's just simply 55%. What if we had 57 thousandths? Right, to a fraction, all we have to do is read it properly. Excuse me. Now remember, 1,000 is just made up of 2s and 5s, and neither 2 nor 5 goes into 57, so this doesn't reduce. I'm just going to leave that. What would this be as a percent? Anyone? $57 thousandths is what as a percent? Uh-oh, am I still live with you guys? You guys still live with me?
Yeah, you.
Okay. Nobody wants to take this one. Oh, there we go. We got, Jimmy says 5.7. Yeah, so again, percent is out of 100. And the hundredths place is right in between here. So that would be 5.7%. Now, a trick that might help in working with percents is going to be related to the next line here. What is 100% as a fraction?
Would it be 1 over 1?
Or just 1, yeah. So it's 100 divided by 100, which is 1 over 1, and 1 over 1 is just 1. So 100% is 1. And that's a pretty useful fact, because if somebody gives me any fraction or decimal, like 0.5 oops, 0.057. If I want to change this into a percent, all I have to do is multiply it by 100%. Now, what is 100% really? It's 1. So all I'm doing is multiplying by 1 here. So it doesn't change the actual value of 57 thousandths. However, what I can do next is leave the percent symbol alone, but carry out this multiplication. Multiplying 100 by 57 thousandths is going to change that part to 5.7, 5 and 7/10, and the percent symbol is just chilling out there. So to convert a percent to anything else, we just replace the symbol with divide by 100. To take a fraction or a decimal and make it into a percent, we just multiply by 100%, do the multiplication by 100, let the percent symbol chill out, because 100% is just 1. Multiplying by 1 doesn't change the meaning of the number, just changes the presentation of the number. So as a decimal, it's still just 1. All right, so here's a tricky one for you. What if we had 1/2%? I'd like you to rewrite that as a fraction and as a decimal. So I'm going to give you guys a moment to do that. What is 1/2% as a fraction and as a decimal? Write something down on paper, whip out a calculator maybe. Love calculators for this stuff. Let's see, my Google calculator has a percent symbol. Oh my gosh, I want to try that. 1/2%. What does that do? 50. Oh, that's weird. Oh, I see what it did there. Okay, that's misleading. Don't use that. All right, anybody want to chime in with a fraction or a decimal that also means 1/2%?
So for fraction, you could put 50/100.
No. That's a good thought, though. That's not correct. What does the percent symbol mean? It means divide by 100. So 1/2% really means 1/2 divided by 100. All right, let's see. How do we divide by 100? Well, with fractions, we could multiply by the reciprocal. What's the reciprocal of 100? Would be 1/100th. So that would be 1/200. So as a fraction, 1/2% is 1/200. Another way to think about it is 1/2 is the same as 0.5. So 1/2% is the same as 0.5%. To get rid of the percent symbol, I just write what it means. It means divide by 100. So what is 0.5 divided by 100? And we learned a trick with multiplying and dividing by powers of 10. You just shift the decimal point. So this shifts the decimal point twice. Dividing by 100 makes it smaller. So that would be 0.005. So as a decimal, we should get 0.005. So remember, 1/2% is less than 1%. So my answer has to be less than 1/100th, right? 1% is 1/100th. 1/2% is less than that. So 1/100th here, 1/2% as a decimal there. Right, so we want to be careful. Although there is a fraction in this percent, until I get rid of the percent symbol, it's not truly a fraction yet. Double check some things here. Proper way to read this number is tenths, hundredths, thousandths. This is really 5/1,000. And I can reduce 5/1,000 by dividing top and bottom by 5. 5 divided by 5 is 1. 5 goes into 1,000 200 times. All right, let's try another one. How about 1/8? So what I want you to do is take the fraction 1/8, convert it to a percent, and convert it to a decimal. So write something down on paper. I'd highly recommend a calculator for this one. All right, so the decimal part is pretty easy. 1 divided by 8 is 125 thousandths. To change either a fraction or a decimal into a percent, the trick is take that fraction or decimal, multiply it by 100%, because you're essentially multiplying by 1. Then, what is 1/8 times 100? Or you could say, how many times does 8 go into 100? That's the answer as a percentage. So let's see, 8 goes into 10 once with a remainder of 2. 8 goes into 20 2 times with a remainder of 4. That's 4 out of 8, which is 1/2 or 0.5. Or shift this decimal point twice. So again, the point of this right here is you've worked with percentages before, you've changed decimals to percent, percents to decimals, and fractions and vice versa. Why do we do things the way that we do? Key facts here. Percent means divide by 100. So the symbol is replaceable with a division by 100. So changing percents to anything else is pretty straightforward. Replace the symbol with divide by 100, clean it up as a decimal or clean it up as a fraction. When you want to go the other way, change either a fraction or a decimal to a percent, that we just multiply by 1 as 100%, right? Multiplying by 1 doesn't hurt. 1 is 100%, right? All we have to do then is clean up the multiplication, leave the percent symbol. And there's a variety of ways to do that. And so that gets us from fractions or decimals into percents. All right, let's do one more and then we'll look at some other problems. Actually, let's do 2 more.
So Gary, I just like to share that my dad is a chemist and he does wastewater cleanup. And I'm telling you right now, these starting to make sense because he had to do salinity factors for the Department of Energy. And I remember him doing all sorts of measurements with scales right down to the hundredths and stuff. So I have a little bit more respect than I might for.
Cool. Nice. Let's take, how about 1/3 the fraction? What is that as a decimal? What is that as a percent? And then (150%) as a fraction and a decimal. So give those two a try. Write something down on paper, whip out a calculator. Come up with your versions of 1/3 as a decimal and a percent, and your versions of 150% as a fraction and a decimal. So if we plug in 1/3 into our calculator, 1 divided by 3, we're going to get a whole bunch of 3s. And they just keep going. So reminder about 1/3. 1/3 is not quite equal to 3/10, or 3 3300ths, or 333 thousandths, right? That pattern keeps on going. That 3 repeats, which is kind of a problem. So we could say it's approximately 0.333. We can put the 3 dots on the end, the ellipsis, to say, it continues like that, or we could put the bar over it. So I think back here in my table, I'm going to rewrite that with the bar over it. But then what do I do for the percentage? So we have a couple of options there. So I could say this is that right there. Could I do this similar thing with the percent? So if I go back here to my scratch paper, to take 1/3 and change it to a percent, I just multiply by 100%, and then I clean up that part. So that's the same thing as dot, 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 times 100%. And multiplying that by 100 is just going to shift the decimal point over. So I get 33.3 dot, dot, dot percent. So I could either say that 1/3 is approximately 33.3%. That's one option. I could say 1/3 is equal to 33.3 repeating percent. But there's another option if I go with the fraction form here. 1/3 times 100 is 100 thirds percent. Right, so that's an answer right there. I could write that. Now, often though, is 100 thirds, is that reduced, by the way? Answer is yes, because 100 is not divisible by 3 without a remainder. So let's take a look at that. 3 goes into 100 how many times? Well, 3 goes into 10, 3 times 3 is 9. Subtract, bring down the 1. 3 goes into 10, 3 times. 3 times 3 is 9. Subtract, bring down the 1. So that means that 100 thirds is the same thing as 33 1/3. So 100 thirds percent would be 33 1/3%. So a few options on how that is. Every one of them is a little weird, a little bit awkward. Which is the best one? I really don't like that repeating decimal thing with the percent. That kind of freaks me out. I like this one better, but I guarantee you if you interviewed 5 different math teachers, they wouldn't agree on which is the best answer here. So I'm just going to pick mine. I think the best answer is when I multiply by 100% and I do division and say that, oh, 100 divided by 3 is 33 1/3, but that's now a percentage. So I think I like those answers the best for that one. 150%, well, that's literally 150 divided by 100, which reduces to what, 15/10? And that reduces a little farther. 5 goes into top and bottom. That would be 3/2 as a fraction. And in this case, I prefer the improper fraction to a mixed number, but we could write it if we wanted to as 1/2. I'm going to say that my favorite answer here is the 3/2. Tomorrow it might be the 1/2. And then as far as a decimal goes, 150 divided by 100, divide by 100 means shift the decimal point twice. That would just be 1.5. So the point of this was just kind of get you comfortable with fractions. Percentages can be represented as a percentage, as a fraction, or as a decimal. And we can have fractional percentages in a couple of different ways, like here and here. And percents can be partial percents, fractional percents in terms of decimals also. So a lot of different possibilities can happen. As far as representing percents with pictures, most common way to do it with kids is to use these 10 by 10 grids to play around with. And then the next activity we're going to do has that idea in mind, where you're going to draw some of these for me. All right, so next is applications with percentages. So how to use percentages in different ways. And percents are usually multiples in situations, but sometimes we use a division to talk about percentages. So just do a few basic examples, then we'll look at some more exciting stuff. So most basic idea would be something like, what is 30% of 70? And of in mathematics usually means multiply. So the interpretation of this one right here is we just want to take 30% and we want to multiply it by 70. 30% is, as a decimal or a fraction, let's go with decimal, 3/10 times 70. And then we can whip out a calculator to find out what is 3/10 times 70. And I think 3/10 times 70 is going to be 21. And I'm curious about that percent button on the Google calculator. I take 30% times 70. Is that what that button's for? Okay. So it just does a divide by 100. 30 divided by 100. Oops, just a digit. All right, so that's 30% times 70. So the percent button is just a shortcut for the divide by 100. All right. And some calculators have a percent button, some don't. There's a lot of TI calculators that have special percent buttons that they have in classrooms, or Casio calculators. The Desmos calculator, I don't know if that one has. Desmos has a bunch of different calculators, a graphing calculator. This one's a scientific calculator. Okay, they do have a percent button. Let's try it. 30% of, oh, that's cute, 70. Nice. I love that they throw the of in there after I hit the percent button. That's so cute. I have to send them a note and say, that's cute. So that's like the most common one. We have a percent of something. So maybe we're talking about a percent off or a percent increase, but we know 30% of 70 is 21. Now, the percent or the base here, any of those could be missing. So I could instead do something like, new question, 21 is what percent of 70? Question mark. So in this case, I'm missing the percent, right? So I can actually translate this the way I see it. 20 equals what percent of 70? And then we could divide the 70 over. Oh, 21, not 20. That didn't look right. I wanted to use the same numbers as above. And a couple options we have to clean this up. We could just plug it into a calculator, ask what is 21 divided by 70. We could reduce it and see what happens. So let's see, top and bottom divide, if we wanted to just stick with fractions, by 7. 21 divided by 7 is 3. 70 divided by 7 is 10. 3/10 as a decimal is 0.3. And then we could rewrite that as a percentage. change a fraction or a decimal to a percentage, you multiply by 100% and then clean up the multiplication, leave the percent. Now, another way all of these work is if you think about the idea of part and whole. So part is some percent of a whole. Part over whole, question mark there, percent, oops, get ahead of myself there. Question mark, part over whole, right? Think about fraction, is what out of 100, right? Percent means out of 100, part out of a whole is a fraction. So any of these can be set up instead of equation-like or recognizing of as multiplication as just a proportion. Part over whole is what out of 100. So I could try that on this one right here. The part is what I'm missing. So maybe I could call that X. My whole is 70. My percent I have, that's 30. And then that's out of 100. We could employ the cross multiply and divide strategy, or we could notice the missing numbers in the top. I simply need to multiply the 70 over the other side. So X is 30 over 100 times 70. So this idea of taking statements about percents, parts, and wholes can be created into a proportion are used often. So this is a pretty popular technique you'll see when you're working with elementary school kids and working with applications of percents. This one down below, we could do the same thing. We just have to identify what's the part, what's the whole, and that's often a hard part. So in this case, it would be 21 out of 70 equals what out of 100. And since the missing number happens to be in the top, we can just multiply by the 100. So then our question mark is going to be 21 times 100 over 70. And we can just use a calculator or do some arithmetic to clean that up. All right, try another one. 32 is 40% of what? So a couple strategies for dealing with this. Translate it directly. 32 equals 40% times what? 40% I prefer to be a decimal. 40 hundredths or 4/10 times what equals 32. And I can just divide by the 4/10. Calculator. Actually, let's set it up the other way and then we'll want a calculator. Alternative is the part whole is equal to percent out of 100. And so we have the part, 32. We're missing the whole, so maybe I'll put a box there for the missing number, is equal to 40 out of 100. Now in this case, the missing number didn't end up on the top, so we do have to cross multiply and divide here. So that's going to give me 32 times 100 equals 40 times my missing number. And then I can divide by the 40. And either of these should lead to the same answer. So let's check them out. So let's see, I had in the first version 32 divided by 0.4, 4/10. So that gives me 80. And then the other version, I had 32 times 100 divided by 40. And I get the same answer either way, so I get 80. These can also be done by drawing pictures of them, and there's a couple of ways that pictures can be drawn. The pictures can either be drawn with the 10 by 10 rectangle square, or we can make a rectangle with chunks of percent. So for these problems right here, I'm going to do the rectangle version. So make a rectangle that's, let's see, 10 wide. So I'll make it, yeah, that's fine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is over there. So what I'm making here is a rectangle that represents 100%. And I did it on this grid so that I can see what 10% looks like. Just double check I counted this right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so I have these 10 slices through here. So each of these slices is worth 10%. Oops. Each chunk is 10%. Now, I also have this 32 and the 40. Well, the 40 would just be down here. So there's 10% there, 20, 30. So 40% would be right here. And the 40% is my 32. So that's also the 32. So 40% is made up of 4 of these equal sized chunks. 32 is also made of 4 of these equal sized chunks. So if 32 is made of 4 equal sized pieces, how big should each piece be? Split 32 into 4 pieces, because that's what my picture shows. How much is each piece worth?
8.
8, yeah, so this piece is worth 8, and that piece is worth 8, and this piece is worth 8. Well, how many 8s do I have altogether here? 10 of them. So that means the total here, the missing number I wanted, is 80. So we can also draw a picture of percentages. Now, can you do that with any percent number? It can get messy depending on the percent that you're working with. But if it's a 40, a 35, something like that, it works pretty straightforward. So let's do another one of those. And let's make this one a little bit more exciting. So let's suppose we work in a store, and that store marks up all items by 35%. So for example, if the store acquired something wholesale, is usually what they pay, prices, $100, then we would take 35% of that, so that would be our markup, which is just $35. So that means the selling price would be $135. So the cool thing about markup, the base, what you started with, is always 100%. And if you increase 100% by 35%, the result is always going to be 135% of what you started with. So suppose, another example, that their wholesale price for something, what they paid, was equal to $160. We could find the amount of markup by just taking the 160, multiplying it by the 35%. Calculator, 160 times 35% is 56. And that was supposed to be $. So that means the selling price is 160 plus 56. What is that, $216? Yep. Now, just to compare to this idea right here, that if we start, whatever we start with is 100% and we added 35% to that, my claim is that if we take that wholesale price of 160 and we multiply that by 135%, remember that 135% is 1.35, 1 35/100ths, then we should get the same number. So let's just double check. So we can put the addition up front if we know 100% is our base. So 160 times 1 35/100ths also gives me that same 216 that I ended up with. So it turns out in a lot of circumstances, it's easier to apply the percent to 100 if it's, say, a markup or a markdown than it is to apply the percent and then do the addition or subtraction. And I could also draw a picture of this. So in this case, let's see, let's sneak that in right here. Do we have enough room? Perhaps. So let's start here. And I want to go 2, 4, 6, 8, subtract 10. I want to do that again. 2, 4, 6, 8, 10. Double check I got that right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'm going to run out of room. Done it. Just slide that over a little bit more. Let's put it right there. All right. So the reason I drew so many lines here is I'm trying to deal with 5% instead of 10%. 5 goes into 120 times, so I wanted 20 divisions here because I want this right here to be 100%. Now I want to tack on 35% to that. So that would be 5, 10, 15, 20, 25, 35. So out here would be the additional 35%. And again, each of these divisions here is 5. So that was important. So I should make a note here. Each square is 5%. Now, I can also relate this back to the numbers I was given. I was giving a starting price of 160. The start goes with the 100, so the $160 goes right here also. So a couple ways to think about this. Every 10%, right, if I split 160 into 10 chunks, 10 tens is 100, that would be each piece is worth 16. If I split it into chunks of 5, that would be 20 times into 160. So what would each chunk be worth? each would be worth $8, right? Again, think about it. 20 times 5% is 100. 20 times what is 160. And so we got 8. So each of these squares here is worth 8. And so I'm just putting on how many more 8s? I counted right. Did I count right? 5, 10, 15, 20, 25, 30. Oops, I missed one. So I got one more 8 over there. So there are 7 8s. So there's an additional 56. Now again, it's easier to use if it's just groups of 10%, like 10, 20, 30, 40, 50. You can easily do it with things like 35%, and you can use other percents too. But if you deviate much from 5 or 10%, the pictures get much harder to draw. And so the 160 plus my 56 gives me the new total of 216. So we can think about it in terms of a proportion. We can think about it in terms of adding to 100. We can think about it in terms of a picture. And I think I'm ready to stop here and talk about the activity. So let's leave this screen. And look at activity 6.3. So the first part of activity 6.3 is pretty straightforward. You're going to draw some pictures, like I drew 65% here. You're going to draw a picture of 33%, 3/10, 1/3, 120%, and 5/4, using the idea of a 10 by 10 grid represents one whole. So you can do that on your own later. This part I want you to group up on. So I have a couple of examples here. We're going to do, we could probably have enough time to do 2 or 3 of these together in groups. So in the first one, I'm doing a similar markup problem to the one I just did, just with some slightly different numbers. So here I used a 40% markup starting with $160, and I go through the picture, the proportion. So I do it in 3 different ways here in this paragraph, kind of like I did earlier. The second example goes over a percent off. So instead of adding to 100, in the one below here, we're taking away from 100. So if there's 75% off, that means you pay 25%. So you pay the blue part, the green part is your discount. And what we want to be able to do is use these pictures and or proportions to find missing numbers. And the missing number could be any of these. It could be the whole that's missing. It could be the part that is missing. Could be the percent that is missing. So any of those will work that way. We're going to use either percent markup or percent decrease for each of these. And so I have a few problems down here, and they start off easier and then get harder. So I'm going to split us into groups right now, probably groups of 3 or 2. And then my recommendation is that in the groups, let's see, do numbers 2 and 3, given the time we have left today. Yeah, that sounds good. So we're going to split into groups. We're going to look at part 2, numbers 2 and 3. One of them is like the example I just did, and then I have a couple of other similar examples here for percent increase, example 1, percent decrease, example 2.